All right, so let me summarize some of the important concepts that we have covered so far. So once again, we started with logistic regression. And from a concept point of view, from a concept point of view, the idea was something like this. We wanted to maximize the probability of recognizing the class. Okay. And remember, logistic regression, we use it for binary classification, even though it can be extended to other classes. Okay. So anyway, the key idea was come up with a loss function, then come up with, identify the problem as a linear or a nonlinear optimization problem, right? So once we came up with the loss function, which was h of x raised power y, 1 minus h of x, 1 minus y, right? And if we are summing it over n samples, so this would be, and this would be I, and I, correct? Okay, so then we discussed that because these are probabilities, and how do we convert it to probabilities? Okay, so over here, we had a summing unit, beta 0, so if we have a feature x1, feature x2, feature x3, and so on, right? Or the way we did it was something like this. Beta 1, beta 2, beta 3, and this was our bias, beta 0, right? So anyway, then how did we convert it to a probability? If you recall, the key concept was we passed it through a sigmoid activation function, right? So this was sigmoid. So this will guarantee that the output over here, which we were referring to the actual output, will vary between 0 to 1. So because in a probability we have between 0 to 1, right? So because we wanted to maximize the probability, as we discussed, what we do is rather than trying to maximize or minimize the sum of all the probabilities for different samples, we do the log likelihood. So we try to maximize or minimize the log of this, right? So the loss function, once we go to the log form, log likelihood, becomes, if you recall, yi log of h of xi, and then plus 1 minus yi log of minus xi, right? So anyway, and then the summation changes to a product. And so this is our loss function. We also discussed that because we want to maximize the probability, but typically in neural networks and deep learning, we always try to minimize the loss. So what we did is we put a minus sign over here. Then as soon as we recognize that this is a minimization problem, okay, we try to then identify, is it a linear type of minimization problem, or is it a nonlinear type of minimization problem? Linear has a closed form solution, so we can convert it to a matrix form and solve it. Nonlinear can only be solved iteratively, right? And because of the logs involved over here, this is a nonlinear problem. And what's the most popular technique for solving a nonlinear problem? Gradient descent. So solved by gradient descent, right? Okay, so once again, how do we compute the derivative? Because in gradient descent, we will need the derivative. So we will start out with some initial beta, then beta minus alpha, which is the learning rate. And then this will be basically the derivative, which sometimes we represent by an inverted triangle. So inverted triangle with respect to beta of loss of beta. So this is the log likelihood. So if we can compute this every time, then we can keep iteratively updating it, and finally it will converge, and that will be our model, right? So as we go through the whole course, because by the end of the course, what I'd like you to do is be able to understand some very advanced, complex optimization problems using deep neural networks. So the concept is extremely critical. Don't worry about the details. How do we get the derivative with respect to beta? Sure, you can go through the handout and review it, right? So once again, let me summarize the idea. Idea was turn it into an optimization problem, right? We want to maximize the probability of recognizing the correct class. Okay, so we express it, as a sum of the whether yi, if you recall, was the expected output. H of x was the probability of recognizing that particular, so this is the actual number. So once we pass it through over here, this is what we are referring to the actual output, which is basically, as you can see, multiply the coefficients by the input, add them up, add the bias, pass it through a sigmoid, and that's what will make it the probability, right? So anyway, once we have come up, so this is the key thing. Once we come up with the goal is to maximize this, or if we put a minus sign over here, the goal is to minimize this. Rest is easy. Compute the derivative of it, keep repeatedly applying it, and we'll be able to solve the problem, right? Okay, so because if you take a look at the expression, for the time being, forget the sigmoid. If you take a look at what is it doing? It is doing A of I, so pretend this was not there, the sigmoid. Isn't it doing x1 beta 1 plus x2 beta 2 plus so on, plus beta 0, right? So from math point of view, that is simply equation of a plane. So if we have two classes, let's say x's and O's over here. So in the end, as we try to classify, this will create a separating boundary, which will be a hyperplane. So which will be simply, for a two-dimensional case, it will be a line. For a three-dimensional case, it will be something like this, a plane. And similarly, in higher dimension, it will be called a hyperplane, right? Okay. So now that we have an idea of logistic regression, next concept that we looked at is problem with logistic regression is it's always separating the two classes by a straight line. Yeah.
So the probability of maximizing the class is only applicable to sigmoid or all the kind of activation functions?
It could be any, sigmoid is not the key over here. The purpose of the sigmoid is to make sure the output is a probability. Varies between 0 to 1. You can come up with some other function. It doesn't look like a sigmoid as long as it forces the output to be between 0 and 1, and it will work.
So there is no need of maximizing the probability over there, right? If we use different type of activation.
No, because we want to recognize, right?
Yes.
We do want to maximize the probability regardless it's sigmoid or not. Otherwise, nobody will use this system. With high probability, it should be able to predict. For example, if somebody gave you an unknown point over here, for high probability, it should be able to predict that this belongs to the X class. It's very similarly, if somebody gave you an O over here, it should be able to, with high probability, able to predict it belong to the 0 class, such that, so coming to over here, if you fed in the data for an X, right, output over here might be 0.89. If you fed in the data for a O over here, output may be 0.13 or something like this. So we do want to maximize that. Otherwise, if it's only recognizing things correctly, let's say 60% of the time as opposed to 90% of the time, obviously 90% is better. Okay. So to emphasize the point again, once we say, okay, we want to maximize the probability, right? Once we come up with the expression for maximization, the reason, once again, we took the log was because this is a probability, like 0.89, right? This part over here, this is the actual output. Same way, this is like 0.13 or something. So even if it's 0.89, if you have 1 million samples, you're adding it up, it will just basically keep getting multiplied. So my mistake over here, I did the opposite over here. This should be the multiplication. This should be the addition. Sorry about that. The multiplication will zero it out, right? Okay. So anyway, bottom line is this creates a linear boundary between the two classes. Okay? How can we? A lot of times the data is not linearly separable. So if the data was more complex, so if the data was something like this, right? And similarly over here, okay, so obviously if we were to come up with a decision boundary, it may look something like this. So how can we do a better job at classifying this type of data, right? So this is where we went to the neural networks, okay? And if I create, let's say, a single neuron neural network, what would it look like? Right? X1, W1, X2, W2, and so on. And 1 and B, right? Okay, at the bottom is the logistic regression architecture. At the top is a single neuron architecture. What's the difference between the two? Suppose we also put activation of sigmoid over here.
Back propagation.
We can also come up with the same way. See, when I computed the derivative over here, the partial L over partial beta, I applied it to the whole expression. But I could have also done it piecewise. For example, here also I could have said SI. So partial L over partial beta. In fact, if you go home, try it as an exercise. Try computing the logistic regression derivative for the loss function as partial, so there will be a loss over here, right? And there will be an actual output over here. So try computing it piecewise. Partial L over partial A over partial S over partial A. And you'll come up with the exact same answer when we did the whole derivative.
Isn't the difference that we haven't defined a loss for the neural network yet?
Yes, very good answer. We do have a loss over here. And it is, yes, and it is the error square.
Yes.
So here, if this is the AI, YI, so here for a single neural network, the loss will be AI minus YI squared. And typically we put a half over here. So anyway, the loss over in the logistic regression is corresponding to the log likelihood. Minimization, the loss over here is trying to minimize the difference between the actual and the predicted output, right? But in both cases, the solution is obtained by gradient descent. So here also we will need partial L over partial beta. Oh, sorry, in this case is W, right? Or W1 or W2. And how will we compute it? Again, partial L over partial A over partial S, and partial S over partial W1 or W2 or B or whatever, right? Okay. So anyway, so both of them look very similar at a single neuron system, right? By the way, could we use this loss over here instead of this loss with a neuron? Sure, why not? Then it becomes the same as logistic regression. So a lot of times, you know, if you search online, what's the difference between logistic regression and a single neuron, they'll say it is the same as a single neuron. But in technically speaking, no. Generally, losses here, error minimization. Loss over here is probability of recognizing the correct class minimization, right? Okay, so now let me come into another interesting part, so that today you guys have excellent idea of why we are doing what we are doing. Okay, so now in the last lecture we looked at general concept of neural networks, right? Where we could have any number of inputs, x1, xn, right? We feed it to what we call the hidden layer. Then we have the output layer, right? So again, it could be 2 neurons, 10 neurons, doesn't matter. All right, let's make it 10 neurons. Let's make it 100 neurons over here, 10 neurons over here. Okay, so in the technical terminology, once again, this is called the output layer, and this is called the hidden layer. And remember, every input goes to every neuron. So if there were, let's say, suppose we were doing the digit recognition, so each digit is 28 by 28, which we will linearize it before feeding it to our neural network. So 28 by 28 becomes 784. And as I mentioned to you, the way we do it is, let's say the first pixel over here is 75, second pixel is 89, so we'll feed 75, 89, right? If we are using neural networks with sigmoid as the activation function, what's the range of values sigmoid takes in or produces? 0 to 1, right? So typically what we do is, before feeding the data to the network, we divide by the maximum value. With the pixels, maximum value is 255. So as we feed it to the network, this will be 75 over this will become 89 over 255, right? Very similarly, we'll go to the last pixel. Okay, suppose that's 123. So we'll feed 123 over 255, right? Then in the next row, let's say it is 98. So then we'll feed 98. So basically we go row-wise, right? Every row, read it, next row. Okay, my question to you is it important to read it row-wise? Can we, because we have to linearize it, can we read it column-wise?
Yes, we have to be consistent.
Yes, correct answer. It doesn't matter whether we read it row-wise, column-wise, as long as you're consistent. Okay. So coming back over here now to our concept. suppose we have 784 inputs, 100 neurons, 10 neurons. All 784 will go multiplied by the weights will go to the first neuron, right? All 784 will go here, all 784 will go over here. So if you take a look at the W matrix, the weight matrix over here, what will be the size of it? 784 by 100, correct? Okay, very similarly, if you take a look at all 100 will go to the first neuron, multiplied by the weights. All 100 will go to the next one. So what will be the size of this weight matrix?
100 by 10.
So 100 by 10, right? Anyway, and then finally we'll produce the sum and the activation and so on. Okay, so last time we discussed that, and again the concept is important, let me clarify that. So suppose we have something like this. Okay, suppose there's a set of weights over here. Okay, let me say W1 for the time being. Okay, so your goal was to find partial L over partial W1. Okay, so remember if there are multiple paths to go from the loss to the derivative we are interested in. For example, in this case, there's one path over here, right? There could be another path over here. There could be, because remember, this feeds to all the neurons. There could be another path over here. So when we are computing this derivative, right? So this will, if I call this path 1, path 2, path 3, as we discussed, this will be partial L over the partial in path 1 plus partial L over the partial in path 2 plus partial L over the partial in path 3, whatever that is, right? Okay, so if we have, let's say, 784, then 100, so you can see, if we were interested in, okay, what is this partial L over partial W1? Okay, I remember this could easily become a nightmare because now from every output through every link over here, the derivatives will get accelerated, right? So this is where last time we came up with the concept of the delta. If we can find delta over here, and what was the definition of the delta? Definition of the delta was it is the derivative from the loss up to that point. So for example, if I call it delta 1, I call this delta 2 as an example. Whatever from here to here, the total derivative of all the paths will be partial L over partial delta 2, right? And delta 2 will be partial L over whatever, suppose this is star in the middle, whatever that star is. Very similarly, if this is double star over here, then delta 1 will be partial L over partial whatever that double. So it will be the accumulation of everything up to the middle of the neuron. Okay. And the benefit of this technique, if you recall, was suppose this matrix is called W1, suppose this matrix is called W2. Then how is W1 related to W2? W1 is simply W2 times delta 2. Okay. When we multiply matrices, we have to be careful about the dimensions. Okay. So let's take a look at the dimensions. What is the size of W2? 100 by 10, right? What is the size of delta over here if there are 10 neurons? 10 by 1. Okay. Now, what's the size of delta 1? 100 by 1. So, if we simply multiply this, will it come out to be 100 by 1? W2 is 100 by 10, and this is 10 by 1, right? So you can see it will come out to be 1. So be careful as you are multiplying the matrices. But anyway, so the neat thing was, if we do the deltas, then this delta is easy. From the loss function, we can go up to over here, then up to the sum to compute delta 2. Once we have the delta 2, all we have to do is multiply by the weight, we'll get the delta 1. Then how will we find out? Let me see if everybody understood last time. How will we find out? Okay, suppose delta 1 we have computed correctly. Our goal is to find out partial L over partial W1. W1 is this, sorry, partial L over, W1, partial W1. So W1 is this whole matrix over here. What is the relationship between partial L over partial W1 to delta 1? So I want to know what should I do to delta 1 so that I can compute this. Suppose delta 1 we've already computed.
Multiplied by x.
Multiplied by x, the previous thing that's feeding over here. So let's multiply by x. Okay, let's check the dimensions. When we do partial L over partial W1, what size do we expect? Same size as the W1, right? Which is, in our example, 784 by 100. Everybody agrees? Okay, now take a look over here. What's the size of x? 784 by 1. What's the size of delta 1? 100 by 1. Can we multiply these two matrices? No. So what should we do?
We do x and then delta transpose.
X times delta transpose. So obviously this is not right. If we did x times delta 1 transpose, then this will come out to be 784 by 1. So anyway, I provided a lot of the code for you guys for assignment number 3. As you go through it, make sure when the transpose is being used and so on, if it makes sense or not, right? Okay. So now, let me cover one important concept before we go further and take a look at something new. Okay, so suppose you're given a problem, and let's take a look at binary classification. And you're given two classes. Let's say X's and O's. Okay, suppose the data looks like this. You plot it, and it looks like this. My question to you is, will you use logistic regression to solve this problem? Can we use logistic regression? Can you figure out a straight line that will give you maximum separation between the data? Logistic regression is always a straight line. Okay, so answer is you can use it, but it will do a poor job, right? So now we need a classification system which can create a nonlinear decision boundary, right? So if we know of some technique which can create a nonlinear decision boundary like this, it will be a lot more accurate.
Professor, can we also, because in this exercise we only have x1 and x2, right? Assuming we have two features, right? x1 and x2.
Right.
Can we create also like polynomial combination of x1 and x2 as ordered variables, and then when we use the linear classification, we will make a curve, not a line?
We can, but like I said, let me answer that question. Okay, the short answer to your question is yes.
Okay.
But we also want to create a system that we can easily solve for the parameters,
Okay.
right? Okay, if we combine, you know, power of x or product of x, remember it becomes a nonlinear problem, right? Unless you exactly knew what is the format of this data, what's the format of the curve,
Exactly.
then you will be able to predict, oh, I need this kind of polynomial,
Okay.
right? But if you didn't know, all you know is data is nonlinear, then what is the best approach? Okay. So the answer. As I mentioned, logistic regression will not work in this case, right? Will neural networks work in this case?
Yeah.
What if, can I create a single neuron network?
In combinations of features.
If I created a single neuron network, will it create a nonlinear boundary?
No.
Answer is no. It's the same as logistic regression, right? So how do I use a neural network? As you can see, the data is two-dimensional in this case, right? So we just have two inputs and a bias. Okay. So there's a couple of possibilities. Okay, one is we use, so this is our output, actual output. Okay. So one is we put a hidden layer. Okay. One neuron in the hidden layer, one neuron in the output layer. Correct? The other possibility is we use two neurons and obviously there will be some weights involved over here. Two neurons in the hidden layer, one neuron in the output layer. Can I keep increasing it? So the question is, how many neurons should we use in the hidden layer? So let me write down the question. One, two, three, four, okay. And the answer is it really depends on the data, right? Okay. So let me demonstrate it to you so that you can visually see what is the effect of what if I use two neurons, what if I use